What?
Okay, I just started recording.
Oh, you're recording. Oh, never mind.
That's right. That's right, as one of the organizers. Yes. Okay. We have to rectify. Okay. Yeah, Mark, we'll rectify that. And we should also get Mark. Mark, we'll also get you on the calendar. There. So let me say a little bit about Vish. Can I have my phone? It helps me keep track of time. So let me say a bit about aviation at Berkeley, right? Like you know that many universities in the world have an aerospace department. Berkeley does not have one, right? Do you think we should have one? Or do you think we do better without one? Do what, Vish? Closer. That I cannot do. I will forget that. We should make it work in future so that this microphone streams through. Yeah, and we'll do that. Mark thinks we should have one. Yes, so there are several of the faculty here today who are actively discussing this question about whether we should have one or not. And so one of the things that we realized is we don't actually have an aerospace seminar at Berkeley. Usually when Berkeley organizes seminars, things are announced well in advance, right? Here the speaker list is still developing, right? And I decided to give the first one because at such short notice, it didn't seem appropriate to invite anyone. And so this thing, but we felt that we should start something, right? So if you're looking at all these teething troubles, it's because it's like everything else at aerospace at Berkeley. It's in a phase now of quick innovation and growth. So we see what happens. And one of the things it all depends on, like every effort at Berkeley, is how desirable is it to our students, right? So the fact that you have come here is one sign of the level of interest. So reach out to other friends of yours, right? And if you find this seminar interesting, keep coming and ask your friends to come, right? And that becomes an important measure of, to what extent we should build an aerospace program at Berkeley and make things work, right? I want to thank our partners at the other end. Yeah. So you see over here some of the people from NASA Ames, and in particular in the center there is Dr. David Bell. Will you wave? There we go. Right. So David is the director of NASA Academic Mission Services, whose role it is to mediate between NASA and the university community. And Dr. David Bell is part of the University Space Research Association, USRA, which has over 100 universities, including Berkeley, within its membership. And this seminar came out of a desire on his side to start a major effort like this at Berkeley to deepen the partnership between NASA, Ames, and Berkeley, right? And so that's why it's being done together. And as I said, some speakers will be over there and we'll be listening here, and some speakers are over here and they'll be listening there, right? So I think it is 11:10 now, and I can officially start, right? So we'll do that. So this is the Aviation Data Science Seminar, and I'm Raja Sengupta. I teach in civil and environmental engineering, and I started working in aircraft. I was wondering if it's before some of you were born. In 1998, 1997 maybe, 1997, 1998. and Mark before that. So this presentation is primarily targeted at you, right? And our NASA friends who are very familiar with aerospace will hopefully enjoy how well their work is being presented and showcased. So this visualizes with a tool from NASA, right, called FAST, the National Airspace, actually the Global Airspace System, right? So the Global Airspace System, can we have these front lights off? The Global Airspace System is a system of amazing complexity. Do you know how many, this is something that Vish just looked up, right? And here are the people who've been organizing this, right? So Pavan is a PhD student in city and regional planning. Professor Hansen, you've already met over there. Vishwanath got his PhD here at Berkeley and now works at NASA Ames. And Pangshin is a PhD student in civil engineering. And Sam, where is Sam? Sam is up at the Lawrence Berkeley Labs and also a PhD student on campus now, right? So that's your core group of organizers here at Berkeley. And, right, so this is a system, and this is a little factoid Vish dug up. Do you know how many people are in the sky at any given time? With this big system that you saw moving? Sorry? Check Fund 24. I didn't understand that. Flight radar. But how many people do you think are up in this? Oh, check flight radar. That should be able to tell us how many people are up in the sky? How many planes are up in the sky? And you can do the math from there. Here we go. All right. This is what I learned at Berkeley a long time ago. The way to do clever things is to listen to you guys. And then I become famous. What was your estimate, Vish? About 1 million people. Right? So there is actually a bigger city than Berkeley up in the sky. Some people call it the city in the sky. This is the reach of global aviation today. Now, essentially, you know, if you look at it in the broad time scale of human history, right, over a 200,000-year time scale, for much of the history of our species, our speed has been the speed at which we walked or ran. And there's a slight slope upward here, right, when Rome started using chariots, but it didn't get that much faster. And this little blip that you see over there, where it kind of rises a bit, that's the automobile. And then you see what goes on, right? Why if I want to capture that top point on the scale, you can barely see the slope on this line. That's aviation, right? And a good way that, you know, that I liked of putting it is when people came from India to the United States, like me, it was a migration. For me, I guess it did turn out to be a migration. I stayed in this country. But what was once a migration is now a vacation. Yeah? And, you know, this is sort of the amazing contribution of aviation. And it's a whole century of innovation. It's a very recent innovation in the history of our species, right? You've flown an aircraft like this, right? We are putting a city in the sky now. That's Sputnik up there. This is SpaceX. You know, this is the NASA low boom hypersonic, right? And then, of course, you know, we have a whole city in the sky. And this has produced a lot of data, right? And data science is something big and innovative and transforming many things. And this is together bringing us to this aviation data science seminar, right? And at some point, we'll have Professor Hansen speak about this in more depth. These are the external speakers, right, who are currently confirmed. And you can see they come from all different branches of it. Some people, some of the, you know, people who will be coming are venture capitalists. Some are people who work in space. Some are people who work in aero. Some are people who are at NASA, right? Some are more big picture. Some are very algorithmic and in the weeds with the tools and the dirty, you know, features of the data and all of that, right? So you'll get a whole spectrum of people in this seminar, and that's the way we're trying to do it. The excitement, I feel that, you know, I mean, the reason that today Berkeley is saying maybe we should rethink what we do in aerospace. Something has fundamentally changed, right? That I think has started, that started with drones, right? So you've got all these projections that, where drones would be in 2015, right? There would be this rapid growth. The reality, of course, is the drone market blew past all those expectations. So even all the pundits who like to hype up the expectations couldn't hype it up enough, right? The reality actually just blew through everything. Do you know who this is? Anybody recognize this man? He's actually, in some sense, the first concrete man who had something to do with this. This is Igor Sikorsky, who founded the Sikorsky Helicopter Company, right? All this stuff, nothing before, stuff like before that didn't fly in cities. This is the kind of stuff that still flies in cities with medevac helicopters and police helicopters and things like that. And other than that, now what's flying around are drones. Do you know who this is? Henry Ford. You know this guy, right? And you know why you know this guy? Because this is a revolution we all know. This is what Columbus Circle used to look like before. It was built for horses. And Henry Ford changed the world to something that's built for cars, not for horses, right? Because the automobile became a consumer product and the helicopter did not. Though they're actually founded within about 20 years of each other, 15 years of each other, right? Do you know these guys? One of them is Frank Wang of DJI, and the other one is Chris Anderson of 3D Robotics, who lives in Berkeley. Do any of you own a drone? Some people do, right? But you're not NASA employees or airline pilots, are you? Right? But you own drones. Because for the first time in the history of aviation, an aircraft is a consumer product. The airline seat has been a consumer product. But typically, you and I don't go and buy an airplane. We buy a car. How many of you own cars? Oh, okay, now we have a lot of hands. Right? Well, by the time this seminar is over, we want to make sure just as many hands go up when we ask how many of you own a drone. Right? And then we'll get DJI to sponsor something at Berkeley. Okay, so I am one of the Cal drone guys. I said I got started in 1998 with this stuff, right? And we did a lot of cool things. So these are 3 drones flying in the California Central Valley, right? And this started because the Navy came to us and said, let me give you the dirty secret of unmanned aviation. It takes 1 pilot to fly an F-16, but 3 pilots to fly a drone. So the Predator and the Global Hawk, when those things fly, there's one guy who looks at the camera in the nose. There's another person who flies the aircraft. And there's a third person who keeps track of the mission. Because the plane's not flying just to, just to avoid mountains and obstacles. That's the job. The plane is flying in order to do something to the bad guy. Right? Or depending on your point of view, do something to the good guy. But, right? But 3 people. So Navy came to Berkeley and said, can you change this to 3 drones, 1 pilot? And we said, how do we do this? So when we got into the business, the Global Hawk had just done its first GPS-guided flight from San Diego to Sydney when the students at Berkeley got into the business. So they didn't want us to do anything with that. They said, can you build the $50,000 airplane? The $50,000 airplane, right? So we said, how can we build? Because the Global Hawk and the Predator were like $5 million airplanes. We want to build the one that's for every fireman. So how do we do it? So this was back in 1998. Did smartphones exist then? No. We had just done fully automated driving. That's how this started. We did fully automated driving, and then we started doing fully automated flying. When we got started in 1998, we did this stuff with vision in the loop. Do you know how much RAM my computer had? Any idea? Give me a guess. 500K. We had 500K of RAM. By the time we were doing this, we were working with the Pentium PC104 stack, which had 1 meg of RAM. So we said the only way to do this, what the military does with, $100,000 cameras from Northrop Grumman, we got to do with a webcam. What the military does with, high bandwidth SATCOM, we got to do with Wi-Fi. Then someone points out, Professor, The Wi-Fi is built for internet browsing. It's not built to control an aircraft. We said, look, it's the only thing that matches the price point. So rebuild the entire protocol stack so it can be done. What the Global Hawk was doing with a whole control room with computers that were hypercooled and all that. When did the iPhone come out? 2006. No, 2008. 8, right? If I remember, I might be wrong, but my recollection is 2008. But anyway, whether it was 2006 or 2008, when it came out, right? About 3 months after it came out, you know what my students said? They said, Professor, this is a Unix box. What? We want to use it to fly a plane. I said, what do you mean? They said, do you want to SSH into it? I said, how do you SSH into it? They said, Professor, can we hack it? I said, hack it. Then we get this stuff. This is a drone using vision in the loop, tracking and exploring a river. First, it's exploring, it finds the river, it locks onto the river, starts traveling. It's mapping it as it's going. As the river curves, it will take the curves. That's the sensor footprint on the ground. They hacked the iPhone, they broke it. They said, it's a Unix box. I can use it to fly a plane. So there we were. What was it then, 500 bucks, 600 bucks? We were using this $500 computer instead of a $1 million computer to fly this thing. And of course, everybody hated us. We were in Wired, we were in Gizmodo, we were in Engadget. Berkeley students hack iPhone to control drone. Don't tell Steve Jobs. Poor Steve Jobs died without ever knowing about our research. So, because when you signed the iPhone, I accept, you had a little, you actually agreed to a little thing that you will not use it to control a car or control a plane, because Apple didn't want to be liable, and they knew it was a Unix box. They didn't tell the rest of us, but they knew that the interface they built was just a layer on top of BSD Unix that was released for free by computer science at Berkeley. They knew that, right? So we have a long history, and then it moves on to, you know, then later we did a lot of things. You can find all this on a website, c3uv.berkeley.edu, the Center for Collaborative Control. You know, we started doing network robotics. This is for the European Maritime Safety Agency in Portugal. You know, Portugal is a country, small country, with large territorial waters, almost the size of the United States, because they used to have an empire, right? And they were like the pioneering explorers that made a route to India, Vasco da Gama, and all that stuff, right? So they have huge territorial waters. What ships like to do, ships have to dump their dirty oil. So they're supposed to go to port and dump their dirty oil and pay to have it dumped. Well, you know, the easier thing to do is go to the territorial waters of Portugal and dump it there, because they're a small country without the money to police their borders. So here we were using drones to work on illegal bilge dumping, right? And if you saw this whole thing run, there are, let's see, let me run it from somewhere in the middle. You know, so that's an oil spill, except, you know, since we're from Berkeley, we're not allowed to do real oil spills. So if you want to do a fake oil spill, the best thing to do is dump 100 kilos of popcorn. And so the drone actually goes and searches for that thing, you know, using machine vision, and then it tells a ship, I found the oil, then the ship goes and drops some submarines in that thing that actually collect samples from that oil. Those samples are then tested against the samples that are collected from the ship to prove it's your oil. And then they get prosecuted in the European Maritime Court, right? And then the big view you were seeing was a satellite that was tasked, so, you know, there's all this stuff and lots of science and computer science and all that. Today, drones are not just about data, right? It's about goods. It's about people. And, you know, and NASA is, of course, the thought leader in all of this, you know, and now you can see, we're not just talking about you getting, at the end of the seminar, you know, I was talking about you get a little drone, right? But here, this is like, you know, maybe next time you think instead of buying your Ford, you should buy an Aeromobile. Or I bought a Toyota Prius, which I feel very upset about, because every time I go park one, I see 4 of them parked next to me. So I'm thinking I should get myself an Aeromobile so I can just take off from my Berkeley parking spot. And, right? And this is really a big ambition. Urban air mobility. the idea that if you want to go from here to San Francisco, don't drive, right? The bad part is maybe I'm saying don't even take BART, right? But fly. You know, and Uber is one of the big companies pushing this idea, right? And so this is very revolutionary, because if you think about aviation, is aviation about urban mobility? Do the airlines move people inside cities? No. Only in emergencies people move by helicopter inside cities. Aviation is about interurban mobility, right? The scale of urban mobility is very, very large. Aerospace companies sell a few hundred aircraft a year. How many cars does Toyota sell a year? A few hundred? No, I think a few tens of million, right? The scales of urban mobility are much, much larger. I don't know what is going to happen to the aerospace industry if it actually succeeds in this dream, right? So let me look at the time and give you just a little bit of what we've been doing here. Okay, I've got some time, right? So one of the things we did was, when we started thinking about all this, we wanted to understand, right? If people use it for data, people use it for goods, what will this system look like? And that was Vishwanath's PhD thesis work, right? It's part of his PhD thesis that he's sitting there. So we did the math like this. We thought about goods. Now, UPS and FedEx move about 27 million packages a day, right? Now, Amazon is a big part of this, right? And Amazon Prime Air, we said, okay, let's see, maybe they get 10% of this volume because it moves by truck. That's 2.7 million packages a day. California is a big state, big economy. Let's say 10% comes here. We get 270,000 flights a day. Let me send half of them to SoCal, right? That gives me 130,000 here in Northern California, 135,000. I'm going to send 35,000 to Eureka County. I have 100,000 flights a day in the Bay Area, right? Now, this is last mile delivery stuff. So it travels 5 miles. Can I make this aircraft go up to 30,000 feet and then travel five miles? No. We are engineers enough to know that makes no sense, right? So this is low altitude stuff. Go up to 1,000 feet, 2,000 feet, maybe 3,000 feet. At 5,000 feet, you're actually already interfering with, you know, the traffic carrying passenger aircraft and all, you know, passengers. And you don't want to mess with that, right? If one of those things fall out of the sky, then it's a horrible affair. So we started thinking, and you know, the Bay Area, of course, at that altitude looks really nice. This is a picture from a Cessna, it looks nice. It looks beautiful if you go up there. Now, this is Vishwanath's simulation. You can see these little green things moving around. There's not much moving around. You may have difficulty seeing those green things. Because this is one day at 1,000 feet, right? You have a few Piper Cubs, a few Cessnas moving around, and you know, not that much happens. This is the same thing with 100,000 aircraft in the sky. If I take that 100,000 a day, which we estimated in a very rough way based on packages, this is what it looks like. You see that cloud on top of San Francisco. 2 aircraft are marked red when they're in conflict with each other. It requires some kind of evasive action, right? And this really opened our eyes and has led to multiple doctoral theses, right? Vish did one. Pavan over there is doing another, right? Sam is looking at this for wildfires. Yeah, there's a whole, you know. So this is one of the things, you know, and we studied it at 100 trips a day, 1,000 trips a day, 10,000 trips a day, 100,000 trips a day to understand where the complexity, where it shifts. And by these various measures, right? So Vish looks at aviation and then tries to figure out how do they measure, how, you know, what are the measures of system performance? And this is, you know, plotting a couple of things, you know, loss of separation, right? You have a concept of safe separation, right? This is not collision. People in aviation don't wait for collision because if 2 things come too close, that's loss of separation, right? So he looks at probably, another thing that he looks at is a measure of what something, you know, we would care about, right? My aircraft is supposed to travel 5 miles to my home, but, you know, is it traveling 6 miles just because it's avoiding traffic, right? And if you look at this graph, what it sort of says that somewhere between 10,000 and 100,000 aircraft, these graphs suddenly explode. The rate of growth changes. You see the knee of that curve. It changes rapidly. So somewhere between them, the system enters some kind of very high complexity regime where it somehow needs to be fundamentally restructured, controlled, managed, where we have to rethink. You can't just rely on intelligence on board the aircraft. Just like on the roads, you cannot. Right? The roads are very carefully architected to ensure that you as the driver never solve more than a 4-vehicle conflict resolution problem. At 100,000, what happens is, this aircraft is in conflict with this aircraft. You try to avoid that guy, you immediately find yourself in conflict with someone else who's already in conflict with someone else. When Vish studied those graphs, he found sometimes as many as 90 aircraft are simultaneously in conflict. Right? Now, if you think of the road, when you're following another car, it's a 2-vehicle conflict avoidance problem. When you're changing lanes, it's a 3-vehicle conflict avoidance problem. The car behind the gap, the car in front of the gap. Sometimes somebody else changes into the same gap, it becomes a 4-vehicle problem, and then you and I get nervous. We probably do something like this, or brake rapidly, or pull off. Right? Now, intersections, sometimes, when they're stopped, when, there's traffic on all sides, you are in a 4-vehicle conflict problem. But then we put a stop sign. Everybody's required to stop. And if it's more than that, we put a traffic light. It doesn't look, I haven't figured out yet how to put a traffic light in the sky. Right? But this has to be thought about. You can't just leave it up to DJI. Right? So the thing that we understood is that once you make aircraft a consumer product, everybody can have one. You get one working for everybody. You really need to now build smart airspace. Airspace that is much smarter than it has ever been. One more way of thinking about it is this. We, the techies, took the $5 million aircraft. Berkeley was dreaming of a $50,000 aircraft. We never dreamt about the $500 aircraft or even the $5,000 aircraft. But the reason you could all buy a drone at the end of this semester is you can buy the $500 aircraft, even the $100 aircraft, right? But here's the other side of that. The tech industry that delivered the $500 aircraft now has to deliver 5-cent air traffic control. Because when you buy an air ticket, $50, $100 of it, right, is ticket taxes and fees, right? Mark approximately that, right? 50 to $100 is ticket taxes and fees. That pays for your air traffic control services, your airport services. Now, when a drone delivers a package, you pay, what, $5 for shipping and handling? $1 for the last mile? How much of that is available for the last mile? $1? How much of that dollar can you take away to pay for the air traffic management services? 25 cents? 20 cents? That's the next problem. 20-cent air traffic control, right? So, and of course, this innovation is accelerating, right? So this is a whole generation of new aircraft, because the stuff that's making the Toyota Prius electric and is driving all the glamour in Tesla, that is turning the auto industry over on its head, it started to hit aviation as well. There's a whole raft of companies now trying to build electric vertical takeoff and landing aircraft. And these are not just electric versions of a helicopter. These aircraft are somehow fundamentally different, because the computational ability we have today is fundamentally different from what Sikorsky had to work with. So we can do distributed electric propulsion. We can build aircraft with up to 24 rotors. We can tilt the wing as this aircraft transitions from takeoff to cruise. We can build aircraft, vertical takeoff and I'm going to answer your question in a little bit, okay? but you're obviously very much on target. And it'll come up actually in something that I'll point out just in a few minutes, right? And then we'll take up your question. We'll have time for questions, and we'll take it up. So, right, so this is what is going on, right? And you just heard. I'm very glad all of you are already thinking about what's coming. What am I leaving out? What am I not talking about, right? So all of this is that this whole innovation, this ecosystem is accelerating. And we are still constrained. You know, so Airbus is building something called the Vahana, right? Which where I come from in Hindu mythology is the vehicle of the gods, Vahana, right? But, you know, we still don't exactly have, we have the energy density now to be able to go maybe from here to San Francisco. But we still don't have the energy density to have enough to spare for contingencies, which the FAA requires, right? So there's some space to go, but we're close, we're getting there. It's getting really interesting. So of course, here at Berkeley, all these guys you're seeing, they get excited and they start thinking about things. And I say, okay, let's work on this. But you know, what we know from history is big things are built in small steps, right? So here you see, right? Aviation starts in the First World War. They come back and it's all a big barnstorming circus. What was aviation? All these pilots come back. The government sits on an inventory of aircraft, which they then sell at firehouse prices, right? $300 an aircraft. And these guys who come back, they buy it and they start doing circus acts, right? And it's very much a high adrenaline business. I mean, every 5 times somebody goes up, one guy dies, right? So this is a super cool way of flying. But you know, but then Henry Ford says, no, the businessmen of America led by Henry Ford says, no, I can make this a business. I don't think it's to be like this. I think I can make it a business. Isn't like playing a slot machine. A business, it's something becomes a business when you can quantify and control the risks, right? Otherwise, you're gambling at Vegas. So he says, I want to make Ford Air Transport, Detroit to Chicago, right? And that didn't go so well, as you can see from the 3 dead. But then, after that came the deployment that really built, that converted a migration into a vacation. The US airmail route from New York City to Washington, D.C., which led people to say, look, aviation is a business. When things are done properly, risks are controllable, manageable, right? This is not like playing Russian roulette. And then the rest, of course, is history. So here, you know, I said, let's take a case study approach to this thing, right? Because if I'm trying to imagine the future, I have more chances of going wrong than getting it right. So we start taking this case study approach. So here's where we started close to home. So UC Berkeley is now discussing opening a new 36-acre campus at NASA Ames, right? There's a discussion ongoing between UC and Berkeley, and UC Berkeley and NASA Ames, and we're all hopeful that it'll happen. And you know what? Do you know the Richmond Field Station? We have 100 acres, 170 acres on the Richmond Field Station. Do you know how long it takes to drive from here to Mountain View now? Do you want to do it? 1.5 hours, right? I mean, I do it, Mark does it, a bunch of us do it. This is not a very pleasant experience. There is a reason why our friends at NASA are looking at us over Zoom, right? And this is what we're going to change. So, huh? Oh, Vish does it daily. What do you do, 100,000 miles on your car a year? Right? Now, NASA Ames also sits on the water, right? So if we start a campus there, how should we move people, right? Where should we build our vertiport? Yeah, on the ground or on the water? And, you know, there are patches, you know, these are some locations. We started looking at how we can site this stuff at the Richmond Field Station, at NASA Ames. And the beauty of it, of course, is, you know, this will be an early deployment. Why not? I mean, I'd like, you know, I'm pitching it to campus. Right? If you're going to start this thing, why don't we open the world's first urban air shuttle, right? From here at UC Berkeley, and you fly over water, right? Which is, I mean, the safest thing to do in some sense, you know? So the motivation, of course, is the misery today, as you pointed out, right? 90 minutes to do this 50 miles. If you open an air corridor, the direct route would be 38 miles, right? But it's difficult to do the direct route because these are all the controlled airspaces around the different airports in the Bay Area, right? And no one wants to take, the first urban air shuttle that's being deployed and have it go right through SFO airspace where, aircraft with 300 people on board are landing, right? I mean, what happens in Iran should stay in Iran. Yeah. So then what we do, so we design this thing, and there is a small little slice of airspace actually between Oakland and SFO, right? Which is out of that, the Class B fully controlled airspace. And if you do that, then, the alternate route, you add 2 miles to the route, which is not so bad. And in the Bay Area, if this ever gets going, that little slice is going to be the bottleneck of the Bay Area. That is where every clever air traffic engineer will have to figure out what to do. Because whether you're Uber or you're Amazon or whoever, all these different fleets that might come in the future will want access to that little slice, that little bottleneck. And then, right, you got to do some trajectory design, takeoff and landing and all that sort of stuff. And Vish does all this stuff. Then he decides to basis, he looks at this, the data from the Airbus Vahana, which they gave us some data. And then, a design, sort of a proto design at NASA that's done by Wayne Johnson on this, 6-seater electric aircraft. Because the other source we had for numbers was the Uber Elevate white paper, right? But, here at Berkeley, we got to make a choice. Do we go with Uber's aircraft analysis or with NASA's aircraft analysis? So I guess we made our choice. And then, here's the kind of, so we looked at what's the demand. How do I figure out how many people are going to occupy 36 acres of the most valuable real estate in the world, right? So I looked at Apple, 175 acres, 12,000 people. So based on that, we said 36 acres, 2,400 people. And then we did the math. If I move if I move them in 2-seater aircraft, and I'll give you the separation numbers and all of that come after that. Their takeoffs and landings 2 per minute, et cetera, right? So when we do all that, right, if I'm running a 2-seater aircraft, I would move 720 people in a 3-hour commute window. And if we're doing the 6-seater aircraft, we'd move 2,160 people in a 3-hour commute window, right? Which is why I say, well, I'd like to tell the campus that it's a deal, but there's more to it than this actually, because here I'm just talking about it can be done. Right? I've got to look at the cost side in order to see if it's a deal or not. But at least I've got a little question mark next to the value. Like all proponents, I'm kind of a little over-enthusiastic. So we say, we have two takeoffs and landings per minute. We have an 18-minute trip time based on 150 miles an hour. And if you take that 2 per minute separation, the number of aircraft in corridor is 36 at any given time when the corridor is full, right? And you have a miles in trail separation of 1.25, which is enough for the jet wash, right? But this, I can assume this, that I'm doing 2 per minute because I'm assuming I'm the first guy doing an urban air shuttle. Berkeley, the first people. So nobody else wants that little slice of airspace except us between Oakland and SFO. But if we really succeed, I mean, there's going to be what, 1 every 2 seconds through that thing? I mean, or we have to push it to something like that. And then the jet wash is the $1 million question, right? So, so then if you look at this from the point of view of the FAA as a stakeholder, of course, right? This can all look like a headache, right? So many new aircraft in an airspace that they don't actually provide separation services for, et cetera, et cetera. From the commuter side of it, this is actually, according to me, the super cool thing, right? So today, if we open a campus at NASA Ames, and I don't want to go 90 minutes, right? There is a way to take me. You can fly me by helicopter. I'm a Berkeley professor, very important guy. The problem, though, is if the chancellor does that, you will be beating down the chancellor's door. You know why? Because if I go in a Toyota Prius or a Tesla, it's going to be, I'm going to expend, even if I convert gasoline, 30 kilowatt hour of energy. If I go by helicopter, it's 250 kilowatt hour. The environmental consciousness of the UC Berkeley campus will not permit the chancellor to fly like that. We cannot do that at Berkeley, right? Yes, we innovate, but we are responsible people, right? But the interesting thing that you see here is not just the time axis, but it's the energy axis. The aircraft are not up there, they're down here. So with the math that we did, if you take a 30 mile per hour gasoline sedan and you convert this using DOE equivalents, you're expending about 35 kilowatt, you're expending about 50 kilowatt. 50 kilowatt hour. If you do it in an electric sedan, it'll be 25 kilowatt hour. You improve by a factor of 2. But if you do it in one of these aircraft, it will be between the 25 and 50. It will not be as good as the electric sedan, but you will not do worse than your gasoline sedan. The helicopter is 250, right? So yes, it is going to be not as green as the electric car, but it's in the ballpark. And there is a difference between 20 minutes and 90 minutes, right? Now we start classes at 11:10, then we'll have to start it at 11:20. And you can take classes there, right? So let me stop here, basically. Okay, so here's some of the other part of the math. So assuming that it's a commute hour, right, and everything moves one way, and they wait there until for the evening commute, I would park 120 to 360 aircraft at NASA A. Right? I don't know what the reaction is at that end. Yeah? And likewise on this side, in the evening commute, I need to find parking for 300 aircraft at the Richmond Field Station. I don't know what the birds there think of that, right? Then there's of course charging, and it's a large capital stock, right? So how does all this money come from? What happens? Is it buying? Is it leasing? Is it renting? Yeah. So all this urban air mobility, right? One of the challenges of this urban air mobility stuff is that it has to service urban mobility, right? Which works for cities, which are growing. And I was in London, right, recently. I want to stop this thing here, actually, right? Because one of the dreams, according to me, when I look at this picture sums up one of the dreams. Do you know the phrase, the wrong side of the tracks? It's been there. It actually wasn't born out of this. It was born out of railways. When railways came into cities, they sliced cities in half. And then either you grew up on the right side of the tracks or the wrong side of the tracks. Later, the same thing happened because of this. When I look at urban air mobility, this is what I see. You know, maybe this is a way to banish this phrase, the wrong side of the tracks, the sociological divides that have damaged our cities, into the dustbins of history. But there's a long way to go. There's a long way to go. When I was in London over this vacation, I meet the Chief Technology Officer of Transport for London, and he says, don't talk to me about urban air mobility. It's a waste of time. So we have a long way to go, right? The value proposition has to be made to the people in London who can choose between ferries, trains, cars, bicycles, Toyota Priuses, and they have to see value in this new thing, this aircraft. But I say, right, in the life of a 20th century city, there's always come a point in the growth of the city where it has to go under. It happened to LA. LA now has a metro. It's happened to the Bay Area. We have BART. It happened to London. You know when it happened to London? 1890 is when the London, I think, or even before that, the London Underground opened. Oh, it's here, 1863. It happened to Shanghai, right? And the results are transformational. But we all know the capital costs of doing this, right? So I will stop with this question. Why have we not opened the great skies above our cities, even as we have sprawled and crawled on the ground? So let me take your questions and questions from our colleagues at NASA. And let me request you to come and to keep coming. I hope I have not made you feel you never want to come again. Yeah. Oh, Mike.
So why does it make sense to have many smaller aircraft going very frequently on this corridor versus a few larger aircraft, which maybe would solve some of the issues with the storage and the spacing and the management of the airspace?
So, see, exactly. The larger aircraft have all the advantages you talked about, right? Why is Uber Pool an innovation when we have buses? Right? So when I started, once I started thinking about this idea, I didn't say, oh, if I'm the only guy who talks about it, it stays like a professor's favorite project. A professor is allowed to say anything. I went to Scott Shackleton, who actually builds the buildings of the College of Engineering. Scott Shackleton immediately said, Raja, give me your business case, your value proposition, piece of ferry. If I'm moving 2,000 people, why should I not run a ferry? Well, one ferry can easily take 2,000 people. What time should I have it go? So that's the problem, right? Large vehicles aggregate people and reduce marginal costs. But if it leaves at 9 o'clock, everybody who wants to go at 7 o'clock has to go at 9 o'clock. How will it shake out? I don't know. All of that is work that remains to be done. I don't think anybody's successfully done that work yet. Been able to say, this thing is not going to be as cheap as doing it. Maybe it's $5 more expensive. Maybe if I try to reduce your wait time to 5 minutes, it's $10 more expensive. Well, are you willing to pay $10 more for a travel time reduction of 20 minutes? I don't know. Maybe that is exactly what the entrepreneur has to figure out. I'm just looking for the entrepreneur. Right? I mean, Berkeley is what now? We are 30 companies behind Stanford. We have produced, we're within the number of startup companies that we've produced by, I think, 30 of Stanford now. Maybe with this, we can cut it to 28, 29. I'll take your question, but I'm going to take your jet wash question first, right? So, do you want to ask do you want to say something more about it?
Would you like me to reiterate it? Or?
No. So you're saying that when you pack these things together,
right? So essentially, I'm not quite sure the mathematics of this, but the more aircraft you have in a concentrated area, I wonder if there's going to have to be an upper limit, precisely because when you induce economies of scale, yes, it brings the cost down, but now, as you said prior, that there's more risk of collision, but also I thought there might be more disturbance in the air, thereby inducing jet wash.
So I actually have the feeling there are better people over there to answer the jet wash question. I can give my speculation. Is it possible for them to answer?
Yes, NASA people can talk with the microphones. But I don't know if anyone has the answer to that question.
Educate the students about jet wash. Where's Gano? Gano's been doing air traffic management all his life without thinking about the jet wash. Gano, I'm sorry to put you on the spotlight.
So, Raja, are you asking about wake vortex, or what are you asking about?
Yeah, exactly. So he's calling it a jet wash. He's saying that, you have these aircraft, you bring them too close, there's going to be a wake vortex problem.
Yes.
So why don't you explain how bad it gets, etc.?
So depending on the type of aircraft and the size of aircraft and its wake signature, there are different separation requirements. And of course, these are electric vehicles, and depending on what type of vehicle it is, for example, if it's a helicopter, it'll have a different kind of aerodynamic characteristics compared to like a fixed wing aircraft. So all the different designs that Raja talked about, those would have different kind of separation requirements, and what they are would have to be determined. For the conventional aircraft, like a 747, 737, Cessna, those things are kind of known. And the air traffic, actually, the current separation is in miles. So, of course, if you want to fly these types of urban air mobility aircraft, the separation would be less than that, because you cannot, the picture that Raja showed about on top of San Francisco, that sort of thing is not possible.
Not possible.
With the current separation requirements.
Yeah. It has to be rethought in some fundamental way. Yeah. There was a question up front there. Oh, so, yes, sir. Go ahead.
Yeah, there's just a follow-up on your slides. I was trying to envision the picture that you're painting, and especially that small corridor between San Francisco and Oakland in terms of public air, or an air corridor that you can use. Seems like air corridor space or channels will be very limited, just like frequencies in radio, as an example. So in this case, would it seem to make sense that you have indeed low density transport but higher frequency? What comes to mind is the People Mover ride in Disneyland way back when, where there was a mechanism of moving people, as envisioned in the Disneyland Tomorrowland concept, to move a bunch of people, but in small batches, so that you don't have to have the big investment of capital like you would talk about it with a ferry or something like that. And which, by the way, they do in Japan, where they reconfigured 747s to transport people back and forth between Tokyo and Osaka on a daily commute basis.
Oh, really?
Oh yeah, I've been on one of them. They're real cattle carts.
You made a note of that? We should look at that. We should look at the economics of that. Yeah, okay. We should research that properly. There was a question up front there. Thank you very much, sir. Yeah, it does. I see the analogy with the People Mover thing, but that 747 thing you pointed out is something we should study if we're going to do work like this, and to understand its economics. I didn't know about that.
So I'm just curious, is the assumption that all of this urban air mobility research and work in the Bay Area, for an example, is the assumption that everything would be autonomous, or that there's going to be a driver in these cases? Because when you're talking 90 aircraft in a conflict resolution problem, how do you do that if it's not autonomous from the start?
So firstly, I'll give you the one or two things I believe, right? So I believe that what we do, okay, before I give you my own opinion, let me actually stress the value of your question, right? So if you go look at, the research plan documents and things that NASA releases on the web, you will see that your question, right? What is this going to be? Is this going to be fully autonomous, partly autonomous? Will these things be like FPV drones flown by, or like Google's been given permission that you can have your car without a driver, as long as you have a reliable high bandwidth video link where you can then drive it remotely? Will it be like that? Will it be really, there's just one person sitting there monitoring 1,000 aircraft, right? So you have asked the $1 million question. And I don't think I cannot give you an answer to that question. The only appreciation I can give you of the magnitude of your question is if you go look at the NASA website and see the strategic documents that they release, you will find NASA has published, with 100 pages of discussion or more, an autonomy roadmap, where NASA is trying to understand how can we proceed if we harness the talent in this 1.6 trillion sector of the economy to this question we're asking, right? So this is what is the role of autonomy in this? For those of you who want to be, who want to work in this field, who are, who want to do new things, who want to try and change the world, autonomy is a perfect place to work. And we'll have speakers who come in this and speak about autonomy, right? The one answer that I would like to give you is that I think what happens in transportation, right, that when you see problems that are of this large dimension, they're computationally very complex. The algorithmic complexity is high, exactly in the sense you are taught in your freshman computation class. I'm teaching E7 this semester. I will discuss computational complexity. Right? It's high in exactly that sense. 2 to the power of 90. That's a very large number, right? So I think what is done in transportation is we respond to it with structure. We build the transportation system in such a way that problems of that high dimension cannot arise. The road is converted into lanes. Cars are given turn signals. Intersections are given stop signs. Bigger intersections are given traffic lights, right? Yeah, that's the one thing I believe. Beyond that, I'm going to leave you to your own scientific work, right? So I think Vish is saying, he's found my Achilles heel. I like talking. So we'll stop here today, right? And you get an announcement about the 29th as to what is happening. But the month of February is full. And we'll take the seminar schedule and we'll publish it shortly, right? So you'll be able to see who's coming when. And there'll be abstracts and things of the talks, so you'll be able to see what's going on. Thank you very much for coming today. And I hope you'll stay with us.
Thank you, Raja.
Let me turn this off. Thank you. If you haven't, put your